Thank you for the introduction. Good morning, everyone. So, if you remember, yesterday I finished by stating and discussing two theorems. First, there was a theorem due to Way and Wilking, saying that if I give you a finitely generated and virtually nilpotent group, then they can find a smooth, complete Riemannian manifold, non-negative Ricci curvature, and fundamental group isomorphic to the group we started from. And second, there was a theorem of Milnor, saying that if you stare at a complete manifold with non-negative Ricci curvature, every finally generated subgroup of the fundamental group has polynomial group of degree n. Okay, so let's start with a very straightforward application of Milnor's theorem. So the corollary says that Z n plus 1, the free abelian group of rank n plus 1, cannot be phi 1 of m for an n-dimensional manifold with non-negative Ricci curvature. Okay, and the reason is immediate. You look at this group, you compute the growth, you check that it doesn't have polynomial growth of degree n, and then you apply the theorem, and the theorem that is going to tell you that this cannot be the fundamental group of such a manifold. Okay, next thing I would like to do is to close the circle, as I promised, and convince you that this theorem, Milnor's theorem, combined with another abstract result due to Gromov in 81, shows that actually, so this theorem is sharp. Okay, and Gromov's theorem says that if gamma is finally generated with polynomial growth, then gamma is virtually nilpotent. Okay, so before I comment more on that, let me mention a refinement. So, of course, if you combine Milnor's theorem and Gromov's theorem, then you easily deduce that any finitely generated subgroup of a fundamental group of a manifold with non-negative Ricci curvature is virtually nilpotent. But before I move on, let me mention a refinement for this statement due to Kapovic and Wilking. 2011, and this is very much in the spirit of two of the other lecture series. So basically, the idea is that we would like to quantify the combination of Milnor's theorem with Gromov's theorem, and what we would like to quantify is this virtually. Okay, so virtually means that it has a finite subgroup which is nilpotent, and we would like to quantify the index of this subgroup. Okay, and the theorem says that if you fix a dimension, then there exists a constant only depending on the dimension, such that if M and G is, as always, smooth complete with non-negative Ricci curvature, and gamma is a finally generated subgroup of the fundamental group, then, okay, well, first, you can bound the number of the generators of gamma. So gamma can be generated by less than C of n elements. Okay, and second, gamma has a nilpotent subgroup gamma prime such that the index of gamma prime is less than C of n. Okay, moreover, you can also bound the nilpotency length of gamma prime. This is less or equal than the dimension. Okay, so let's see again another straightforward application of this refined statement, which doesn't follow from the previous ones. Okay, so you fix the dimension again. You fix your favorite integer, your favorite natural number, greater or equal than 2. So this is natural. Then there exists capital N, depending on n, such that if you look at the direct sum of z over kz, z over kz, okay, and you take capital N copies of it, okay, this cannot be the fundamental group of an n-dimensional manifold with a negative Ricci curvature. Okay, so note that this group is finite. Okay, so the growth is trivial. Okay, however, it has too many generators. Okay, and therefore you can apply Kapovich and Wilkie's theorem, and their theorem is going to tell you that this cannot be the fundamental group of a manifold of dimension n with non-negative Ricci curvature. Okay, any questions? So you see that the picture is pretty sharp about fundamental groups of, so our knowledge about fundamental groups of manifolds with non-negative Ricci curvature is pretty sharp, modulo a condition, okay, which is this finitely generated condition. Okay, and this was kind of a strong motivation for addressing a conjecture that Miller made in the same paper where he proved this theorem, where he asked whether the fundamental group of a manifold with non-negative Ricci curvature should always be finitely generated. Okay, and so today I'm going to start by discussing a few methods known for proving that fundamental groups of manifolds in this context are finitely generated. Okay, and then we're going to spend the remaining two lectures, the last part of this lecture and the remaining two, outlining the construction of a counterexample.
Okay, we move to the next topic. The Milnor theorem, basically talk about the growth of the fundamental group, is basically why is the Ricci curvature is used. Is for the volume growth and Bishop theorem.
Yeah.
Can you tell in a nutshell where Ricci curvature is used in the Gromov?
So Ricci curvature is not used in Gromov's theorem. So Gromov's theorem is completely abstract. Okay. You pick a finitely generated group.
Right. In Kapovich-Wilkin, yeah.
Okay. Okay. So in Kapovich-Wilkin, you said. Okay. How it is used? So very roughly speaking, so the rough, a very imprecise outline, so a very imprecise idea for the proof is that you try to argue by contradiction. Okay, and so Ricci curvature is used via Gromov's precompactness theorem to be able to pass to the limit inside the contradiction argument. But this is just a very imprecise idea. But the starting point is that you have use Ricci curvature to get compactness. You use compactness, precompactness, and you use precompactness inside the contradiction argument. Any more questions? Okay, so the next chapter is going to be methods to prove finite generation of phi 1 of m. Okay, and let me start with the very general and powerful construction due to Gromov. This is the so-called construction of Gromov's short generators. Okay, so it is simple. You have M and G complete, and you look at the universal cover. Phi from M bar to V bar to G. Okay, and you fix a base point X bar in M bar. Okay, now so you'd like to find a sequence of generators for gamma, which is the fundamental group, which as yesterday we were viewing as a subgroup of the isometric group of M bar. Okay, and you proceed as follows. So you choose gamma 1 in gamma, such that the distance between gamma 1 of X bar and X bar is the minimal one. So the displacement of gamma 1 is the minimal possible. So this is the mean among gamma in little gamma in capital gamma of the distance between little gamma of X bar and X bar. Okay, then you proceed inductively. So you choose gamma I plus 1 such that the displacement of gamma I plus 1 at the base point is the minimal one. But now you need to subtract from gamma the subgroup generated by the previous guys in the sequence. So this is the minimum when gamma ranges in capital gamma minus the subgroup generated by gamma 1 dot gamma I of the displacement of gamma X bar X bar. Okay? Any questions about the construction? So, two remarks. So, okay, so the first remark is that so the gamma i's are not uniquely defined. Okay, but we don't care about that. Okay, and the second point, this is clear, is that so the sequence gamma I generates gamma. Okay, and in particular, if the sequence has only finitely many elements, your group is finitely generated. Okay, so if the construction of Gromov's short generators finishes after finitely many steps, we have proved that the group is finitely generated. Okay, let's see a context where this can be made to work. So Gromov used this construction to prove this theorem. So if M and G has non-negative sectional curvature, then phi 1 of M can be generated by less than a constant only depending on the dimension, which is 3 to the n. Okay, so let's discuss the proof of this theorem. Okay, note that sectional curvature, non-negative sectional curvature is stronger than non-negative Ricci curvature, so this is a special case of the general setting we care about. Okay, so we look at Gromov's short generators. Okay, and the observation is the following. The first observation is the following. So I claim that the distance between gamma I of x bar and gamma j of x bar is greater or equal than the maximum between the distance between gamma I of x bar and x bar and the distance between gamma j of x bar and x bar. Okay, and this is true for any I different from j. Okay, what's the reason? So this doesn't use any curvature assumption. It's just a consequence of the way the clever way you choose the short generators. Okay, so the reason is that gamma I is an isometry. Okay, in particular the distance between gamma I of x bar and gamma j of x bar. Okay, this is equal to the distance between x bar and gamma I to the minus 1 of gamma j of x bar. Okay, I am applying gamma I to the minus 1 and using that it is an isometry. Okay, on the other hand, suppose that j is bigger than I. Okay, then this would be greater or equal than the distance between x bar, gamma j of x bar, and so suppose it is not, this will be smaller than the distance between gamma j of x bar and x bar. Okay, and if you look at the way Gromov's short generators are chosen, okay, this would imply that gamma I to the minus 1 times gamma j belongs to the subgroup generated by gamma 1 dot gamma I gamma j minus 1. Okay? Okay, the reason is that this is an element of the group, gamma I to the minus 1, gamma j is an element of the group. If the displacement is smaller than the displacement of gamma j, then when it comes the time of choosing gamma j, I could choose gamma I to the minus 1 composed with gamma j instead. Okay, but now, so gamma I also belongs to this subgroup, and therefore I can compose with gamma I on the left, and I get that also gamma j belongs to gamma 1 dot gamma j minus 1. Okay, and this is a contradiction. Okay, so what I got is that if I look at the triangle, a geodesic triangle with vertices x bar, gamma I of x bar, and gamma j of x bar. So let's draw a picture here. So here is x bar, here is gamma I of x bar, and here is gamma j of x bar. Okay, so there is a relationship between the sides of this triangle. Okay, and the observation now is that if you draw a triangle with these sides in R2, so then what happens is that this angle here should be greater or equal than 60 degrees. Okay, but now you can use Toponogov's triangle comparison. Okay, so sectional curvature greater or equal than 0 implies via Toponogov's triangle comparison that the angle that you see in the manifold between these two geodesic segments is larger or equal than the angle that you see at the level of the comparison triangle in R2. Okay, so this implies that the angle between gamma I, x bar, gamma j, x bar, and x bar is greater or equal than pi over 3. Okay, and now the conclusion is elementary. Okay, you only need to check that there cannot be more than 3 to the n vectors in Rn whose pairwise angles are greater or equal than pi over 3. Any questions?
Is that a geometric fact obvious?
So it's not obvious. So which factor?
The number of factors in Rn with pairwise angles.
Okay, so it's not obvious, but the proof is not difficult. I will leave it to you as an exercise. Any more questions?
Is that a sharp bound? Like
I don't think so. I don't think so. But the most important consequence for us is that there is a bound. In particular, this implies that the fundamental group of any manifold with a negative sectional curvature is finally generated.
So the first theorem by Wilkin, basically, can we not have the assumption there for the fundamental group to be finitely generated?
Can you say it one more time?
So in the first theorem,
The one
not this one, the one you just erased by Wilkin, like the lecture.
Okay.
So we had the assumption of finitely generated. So
Yeah.
in many cases, we can just forget that assumption as well. So we will get a stronger statement, right?
So you're asking whether, so from Way and Wilkins' theorem, if I drop the finitely generated assumption, then I can build a manifold. This is known only in certain cases. Okay, I will comment on that later. So if you give me a virtually nilpotent group, okay, in general it is open whether you can find it. So there need to be extra conditions, okay, and for instance on the number of generators and something like that, of finally generated subgroups, but in general it is open whether you can find the complete manifold with a negative Ricci curvature and that fundamental group.
In the Kapovic-Wilkin result, the constant n which bounds the nilpotency index is not explicit.
It's not explicit.
Exactly.
Yeah. Thank you. So let's see. So the next, the second and last method that I would like to discuss to prove finite generation in this context, it requires some background. Okay, so first it requires another theorem of Wilkin from the same paper. And curvature doesn't matter for this theorem, it's just a theorem about abstract groups. Okay, and it says that if gamma is a group such that every finitely generated subgroup gamma prime of gamma as polynomial group of degree less than n, less or equal than n. Okay, so here n is fixed. Then gamma is finally generated if and only if every abelian subgroup of gamma is finally generated. Okay? And note that the fundamental group of any n-dimensional manifold with non-negative Ricci curvature has this property because of Milnor's theorem that we proved yesterday. Okay, and let me rephrase this by saying that so if you if you are trying to prove the Milnor's conjecture, the conjecture of Milnor, so the fundamental group of a manifold with non-negative Ricci curvature is finally generated. Okay, basically we could rephrase this by saying that you only care about abelian groups. Okay, and the second tool that we're going to need is the content of an exercise that I leave to you. Okay, so and the exercise has two parts. Okay, part A is the part we're going to use. So, and it says that if gamma is finally generated and virtually nilpotent, then any subgroup is finally generated as well. Okay, and part two is easier, but we won't need it. Okay, so it asks you to check that for part A you really need the assumption that the group is virtually nilpotent. Okay, so find a subgroup of F2. So this is the free group with two generators, which is not, and of course this is finally generated. However, it has a subgroup which is not finally generated. Okay, so now I can state the theorem. Okay, and the theorem says that if M and G is as non-negative Ricci curvature and phi 0 of the isometry group of the universal cover, which is defined as the isometry group of the universal cover modulo the connected component of the identity. If we assume that this group is finally generated, then the fundamental group of the manifold is finally generated as well. Okay, so as I said, this guy here, this is the connected component of the identity. Okay, and note that the connected component of the identity of any topological group is a normal subgroup of the topological group, and therefore this is a normal subgroup, and this quotient is a group. Okay, so it makes sense to say that this is a finally generated. Okay, any questions on the statement? Okay, so let's see how this is proved. Okay, so there are two cases. Okay, case one is kind of a warm-up. Okay, so assume first that the isometry group of the universal cover is connected. Okay, and with the notation that I introduced, this is equivalent to say that the connected component of the identity is equal to the isometry group of the map. Okay? So by this theorem, previous theorem of Wilking, okay, we can assume that gamma equal to pi 1 of m is abelian. Okay? But now gamma is a discrete abelian subgroup of a connected Lie group Okay, so the fact that the isometry group of any complete Riemannian manifold is a Lie group is a theorem due to Myers and Stingrod in 39. Okay, and discrete means that the induced topology is the discrete one. Okay, and now we can apply a deep theorem and an abstract theorem of Mostow, who prove that a discrete solvable group, subgroup of a connected Lie group is always finite generated. Okay? So if you don't know what solvable means, it doesn't matter. So the only thing that matters is that abelian implies solvable. Okay, so we can apply Mostow's theorem, and this is going to tell us that gamma is finite generated.
May I ask, why do we know that gamma is discrete?
So this is a general fact about fundamental groups viewed as isometric as subgroups of the isometric group of a Riemannian manifold. Okay. Any more questions? Okay, note that discreteness here is crucial. Okay. So the group of rationals is a subgroup of the reals. Okay. So this is abelian. This is a connected Lie group. Okay, the induced topology is not a discrete one, and Q is not finitely generated. Okay. Okay. So now back to the general case. Okay. To start, I'll leave you as an exercise to check that using Milnor's proof, that phi 0 of iso 0 of m of iso phi 0 of iso m bar as okay, sorry, every finally generated subgroup of phi 0 of iso m bar as polynomial growth of degree less or equal than n. Okay? So this is just a slight generalization of Milnor's theorem that we discussed yesterday. Any questions while it is?
Why can we assume without loss of generality in the first case that gamma is abelian?
So the reason is Wilkins' theorem. Okay, Wilkins' theorem tells you that if gamma is not finally generated, okay, then there is a subgroup of gamma which is abelian and not finally generated. Okay, we can run the proof with apply to that subgroup. Okay, and we will get a contradiction. Okay, and this is going to tell us that indeed gamma was finally generated. Okay.
Right. So you mean like you use that subgroup and to get a different you use a different manifold with the same universal cover.
Exactly. Yeah.
Okay.
Okay, so thanks to the exercise, we know that pi 0 of Hausdorff and bar has the property that every finally generated subgroup has polynomial growth of degree less or equal than n. Okay, so if we assume, as we are doing, that pi 0 of Hausdorff and bar is finally generated, okay, then Gromov's theorem implies that it is virtually nilpotent. Okay, now we can set gamma 0 to be gamma intersected with the connected component of the identity. Okay, and note that by the first part of the proof, gamma 0 is finally generated. Okay, now we look at gamma modulo gamma 0. Sorry, this is isomorphic to gamma modulo pi 0 of m modulo iso 0 of m bar. Okay, and this I can view as a subgroup of iso m bar modulo iso 0 of m bar. Okay, which is pi 0 of iso m bar. Okay, but I noted before that this is virtually nilpotent and finally generated. Okay, and the exercise here says that a subgroup of a finally generated and virtually nilpotent group is finally generated as well. Okay, so exercise implies that gamma mod gamma 0 is finally generated. Okay, but now, so the conclusion is immediate. So I want to prove that gamma is finally generated. I found a subgroup, gamma 0, which is finally generated, such that the quotient is finally generated. Okay, basically I just need to put together all the generators, and I'm gonna get that gamma is finally generated as well. So if you don't believe me, you can check it yourself. Okay, any questions?
What does gamma mod iso 0 mean?
So
it's not a subgroup of gamma. In the
So they are isomorphic. So here I'm using that gamma mod gamma 0 is gamma mod gamma intersected with iso 0. Okay, and now I can also view gamma as a subgroup of iso of m bar. Okay, and now it follows that these two groups are isomorphic.
no, but how do you say? Iso 0 is not a subgroup of gamma.
So, but you can identify them. Okay, so you can view gamma is a subgroup of iso of m. Okay, and now so I can take there is an isomorphism between the two. Okay, so there is an isomorphism between this group and this group. Okay, which you can define. Okay, yeah, thank you. Any questions? Okay, so for the rest of the lecture, so I would like to start introducing the counterexample, a counterexample. So I would like to introduce the construction of a counterexample to the Miller conjecture that was predicting finite generation of any of the fundamental group of any manifold with non-negative Ricci curvature. So let me start from the statement. So this is from joint work with Elia Brouet and Aaron Neighbor 2 years ago. Okay, and the theorem says that there exists M7 G with non-negative Ricci curvature. Okay, and phi 1 of m is the group of dyadic rationals modulo 1. Okay, so what does that mean? Okay, so I look at the circle, which I identify with R modulo Z. Okay, and I consider gamma, which is a subgroup of this circle, and gamma as a set is the set of all rationals which can be written with the denominator which is a power of 2. So this is the set of L divided by 2 over K, such that K belongs to the naturals, and L is greater or equal than 0 and less or equal than 2 to the K minus 1. Okay? So the first observation is that gamma is not finally generated. Okay, and given that, in particular, this is providing a counterexample to the Miller conjecture. Okay, let me briefly remark on the state of the art. Okay, so the fundamental phi 1 of m and for m and g with Ricci greater or equal than 0 is finally generated. So let me do it like this. So for n equal to 1, this is trivial. In particular, it's finally generated. So it's trivial. I mean that so the study of those fundamental groups is trivial and they are all finally generated. N equals to 2, they are all finally generated. This is due to Cohn-Vossen in the 30s. Okay, N equal to 3 is more delicate, but still the statement is true, so they are all finally generated. This was proved by Liu in 2013. Okay, for n equal to 4 or 5, this is an open question. Okay, and for n equal to 6, we construct similar examples. Okay, and in particular for all n greater or equal than 6. Conjecture doesn't hold. Okay, so on another note, so this group has nothing special. Okay, so with similar constructions, we build M6 or 7G with Ricci greater or equal than 0, and pi 1 of M isomorphic to the rationals modulo the integers. Okay, and once you're able to do the rationals modulo the integers, you can do any subgroup of the rational modulo the integers. Okay, and of course the case that I stated is a straightforward corollary. Okay, but it's easier in terms of presentation. Any questions?
May I ask, is there some deep relation of this exponent 6 and 7 with some other counterexamples in GMT maybe?
Not that I'm aware of.
Also for dimensions 8, 9, and so
Yeah.
on. So is your construction valid for?
Yeah, so there is an almost trivial way to extend the construction to higher dimensions. Okay, you can pick the example, let's say in dimension 6. You want to build an example in dimension n greater or equal than 6. Then what you do is you take the product of the counterexample in dimension 6 with a Euclidean factor of the correct dimension. Does it answer?
Yeah. And what is the difficulty to go to dimension 4 and 5?
So we will see. So we will see the ingredients of the construction, and you will see that. So some of them they do not have a clear counterpart in lower dimensions. So it is likely that if counterexamples exist in dimension 4 or 5, then one has to really change the construction. On the other hand, so I will focus on the 6-dimensional construction because it's easier in terms of exposition, but the construction in dimension 6 is just slightly more technical, but the main ideas are really similar.
So what goes in the n equals 3 case? What does one do?
So in the n equal 2 case, so let me briefly comment on that. So Ricci curvature is the same as sectional curvature. So that's Gromov's theorem, and it was known much before. In dimension 3, so the proof really heavily hinges on the relationship between minimal hypersurfaces and Ricci curvature lower bounds, and you can only use minimal hypersurfaces. You can use very well minimal hypersurfaces to study fundamental groups only in dimension 3. Any more questions?
This is already very well known, but like if the manifold is closed, does that already tell you that the fundamental group is finally generated?
Yeah, that's true. So if you have a compact Riemannian manifold, so you don't need any curvature assumptions. Okay, if you have a compact Riemannian manifold, then the fundamental group is finally generated. Okay, and one way to see that is you look at the universal cover. Okay, and if you run, for instance, Gromov's construction, you're going to be able to check that, so the generators that you need to generate the group, they all have displacement which is less or equal than 2 times the diameter of the quotient manifold. Okay, and since the group is discrete, there can only be finitely many generators within that ball. Okay, any more? Okay, so let me conclude with an exercise. So let me conclude this part about comment with an exercise. Okay, so the exercise asks to construct M8G with Ricci greater or equal than 0 and phi 1 of M isomorphic to the rationals this time. Okay, and I'm not asking you to start from scratch. You could, if you like, use a counterexample with group isomorphic to Q mod Z exists in dimension 7. Okay, so if you go up 1 dimension, there is a bit more space, and you can drop the modulo the integers part. Okay, so and a last comment. Okay, the comment is a bit naive. Okay, that the point that I would like to make is that this choice for the fundamental group of the counterexample is this kind of choices is the easiest one could come up with. Okay, so in particular, so of course any such gamma in Q mod Z, okay, is abelian. Okay, and therefore it satisfies Wilkins, so morally it satisfies Wilkins restriction that we discussed before. Moreover, any finitely generated subgroup of gamma is generated by just one element, and it is cyclic. Okay. Okay. Any questions? So in the last, let me use the last minutes to try to put you into the right mindset. Okay, and discuss a construction which doesn't care about curvature and Riemannian matrix. So I would only like to discuss a classical construction of a topological manifold. So construct N3 topological manifold, no compact, with phi 1 of M3 isomorphic to, let me call it gamma tilde. Okay, and gamma tilde is the group of dyadic rationals. Okay, so same as before, the only difference is that I'm dropping the modulo the integers part. Okay, and as before, this group is not finally generated. Okay, the construction is due to Stingrod, who actually credits Vietoris for the idea. And this goes back to the Forties. Okay, and it starts as follows. So you pick T1 inside R3 to be an embedded, unknotted solid torus. Okay, so here is the picture. This is T1. Okay, this is R3. Okay, and let N1 be the complement of this solid torus. Okay, now note that the fundamental group of this complement is isomorphic to the group of integers, okay, and it's generated by the loop going around 1. So let me call the generator gamma 1. Okay, now you proceed as follows. So you let T2 be embedded solid torus, embedded unknotted solid torus inside T1. Okay, however, I would like T2 to wrap inside T1 twice. Okay, so you draw a loop, which is wrapping inside T1 twice. Okay, and you fatten it a little bit to get the two torus. Okay, now let N2 be the complement of this new two torus. Okay, and for the same reason as before, the fundamental group of this guy is isomorphic to the integers. And let me call the generator of this fundamental group gamma 2. Okay, this is the loop going around the second two torus once. Okay, now what happens is that you know that N1 is freely included into N2, and this implies that there is an inclusion from the fundamental group of N1 into the fundamental group of N2. Okay, so the tricky thing is that this inclusion is not trivial. Okay, so this inclusion in particular is not surjective. Okay, and what happens is that this I will leave you to think about. What happens is that the generator of the second fundamental group, okay, does not get into the generator of the previous one. What happens is that you need to take the power 2 of the new generator to get the old one. Okay, and then you proceed inductively, defining Pi and I as before. Okay, now you set T to be the intersection over the naturals of Ti. Okay, this guy is called the dyadic solenoid. Okay, and you set N to be the complement, or equivalently, this is going to be the union of the NIs. Okay, and this, for obvious reason, this is called the dyadic solenoid complement. Okay, morally, you're just passing to the limit the inductive construction we went through. Okay, then the claim, which I leave you to check as an exercise, is that phi1 of n is indeed isomorphic to the dyadic induction. Okay, this is an open manifold, and so we found an open manifold, open free manifold with fundamental group which is not finally generated. Okay, and so this idea that we proceed by induction and then you kind of pass to the limit. Okay, this will be, as far as I know, this is the underlying idea of any construction of manifold with infinitely generated fundamental group, and in particular it will be the underlying idea, one of the underlying ideas of the construction of the counterexamples to the linear projection. Any questions?
Thank you very much.